Welcome to the Foundry by Forge College for this explainer. Okay, so in our last session, we watched Firedancer absolutely guzzle data like a fire hose, right? Just a massive, high-speed ingestion conveyor belt. Well, today, we're shifting gears. We're stepping away from that raw speed and diving into the meticulous, frankly kind of obsessive-compulsive world of consensus mechanisms. Today, we meet the strict micromanager of our factory floor, the rulebook that dictates exactly when that high-speed line is actually allowed to move.
We've got a really tight blueprint to get through today. We're going to map out the consensus traffic cop, look at timing and coordination, dodge some real-world latency traps, dig into the consensus bridge code, weigh the ultimate trade-off, and finally, look at mitigations and next steps to keep things running smoothly.
So, let's just jump right into it with our first major component, the consensus traffic cop.
Now, in a lot of Web3 models, people tend to think of consensus as just a rubber stamp at the very end of the line. Just a guy at a desk saying, yep, looks good, send it. But in Firedancer, not even close. Consensus is the ultimate micromanaging boss, and it wears two distinct hats. First, it operates as a temporal controller. Its job is to make absolutely sure that batches are sealed on the exact proof of history clock tick. No sooner, no later. Second, it acts as a coordination protocol, which means it's constantly gossiping with peer networks to ensure everyone is on the exact same page. So here's the kicker. This boss doesn't care if your local assembly line is breaking land speed records. If that clock hasn't ticked, or if the network hasn't gossiped back, your entire factory line grinds to a dead halt.
Which brings us perfectly into the mechanics of timing and coordination, specifically looking at active and reactive delays. Let's draw out the schematic of where these stressed-out middle managers cause literal traffic jams in our data flow. Take proposal timing, for example. The consensus mechanism uses a batch flush hook to interface directly with the data manager. The impact? You get alignment delays. Your queue suddenly swells up because the system is just standing there, tapping its watch, waiting for that perfect POHOC tick. Then you've got vote aggregation. The vote collector is constantly reading snapshots, which causes a reactive delay, essentially back pressure straight onto your outbound queues. And the snapshot trigger, it literally blocks new entries until all the paperwork is perfectly filed. All of this stalled ingestion directly translates into longer tail latency for your transactions.
Of course, mapping it out perfectly on a schematic is one thing, but what about real-world latency traps?
Because on paper, everything we just talked about sounds perfectly fine. But in a live Firedancer node during a chaotic shift with frequent leader rotations, that is where we hit the traps. Picture the proposer desperately trying to produce a block, but signature verification is heavily CPU-bound. Your threads get saturated, they're overworked, and boom, your batch completely misses its timing window. Toss in a little network variability where you haven't received enough peer votes in time, and suddenly the proposer has to make a totally blind fork choice. When that happens, you're looking at forced retries and worst-case scenario, complete fork choice rollbacks. If you were watching your telemetry dashboard right then, it honestly looked like a horror movie. Spiked CPUs, massive pileups of unverified transactions, and absolutely screaming outbound latency.
So, how do we actually write the rules for this? Let's look at the Rust code blueprint for what we'll call the consensus bridge.
We can translate all these abstract headaches into a highly practical 4-step assembly manual inside the code. Step 1, prep the batch of pending transactions. Step 2, check the clock and wait for the tick. Step 3, seal it up into an official ledger entry. And Step 4, fire off the vote aggregation asynchronously. Honestly, it's beautifully clean, minimalist logic. But it hides a massive, massive trap.
I want you to pay really close attention to Step 2. That wait for tick function? That is the explicit synchronization point. That is where our temporal controller literally throws up a stop sign and forces an active delay on the entire system. If you're an engineer inserting a timeout here, you are making a critical, cluster-defining architectural decision. If you set a really short timeout, sure, the line keeps moving lightning fast, but you are drastically increasing the chance of building bad data that the network is just going to reject anyway, which forces a super messy replay later on.
And that singular line of code leads us straight into the ultimate trade-off, liveness versus consistency.
Because here's the harsh reality of the engineering dilemma. You simply cannot have infinite speed and perfect safety at the exact same time. You have to choose your fighter here. Are you optimizing for liveness? That's the cheetah. It is incredibly fast, sealing batches instantly for lower median latency. But it's speculative. It comes with wild variance and the occasional faceplant when you guess wrong on a fork choice, meaning a high replay risk. Or do you want consistency? That's the tank. It's slow, it's steady, it waits for full vote aggregation for predictable finality, but that safety net costs you. It brings increased latency and demands way higher memory usage. Fully understanding this specific trade-off is what's going to dictate your entire hardware budget.
But hey, we're engineers, right? We don't just accept bottlenecks. Let's talk mitigations and next steps.
Thankfully, we aren't completely at the mercy of this strict protocol. Firedancer gives us some incredibly powerful operational knobs on our control panel to fight back. If prepping batches is lagging, what do? We crank up parallel verification for the pre-seal phases. If waiting for ticks is causing stalls, we can write logic for adaptive tick alignment windows that actually flex based on real-time network health. And if sealing is spiking your CPU, you just completely offload that to a dedicated thread pool. You can even implement speculative proposal fallbacks. The point is, you treat these patterns as your personal toolkit to balance speed, cost, and safety.
So as we wrap up this explainer, I want to leave you with a question. When you sit down to configure your cluster, which trade-off are you going to choose? Are you going to bet the farm on the cheetahs, or are you going to build the tank? Because getting this balance wrong won't just slow you down, it could literally cost you your stake. To master these advanced concepts and dive way deeper into Firedancer validator architecture, make sure you visit forge.college. Thank you so much for joining me for this explainer from the Foundry by Forge College, and I will see you in the next one.